All right, let's talk about the periodic table. We're going to zoom in on group 13. Now, it might not be a group you hear about all the time, but trust me, it's got one of the best family dramas in all of chemistry. And it all revolves around its rebellious oldest child, right at the top. And that's really the big question we're tackling today. How does one element just decide to break all the family rules? We're going to unpack the story of this chemical family, look at the patterns you'd expect to see, and then focus on this one element at the top that seems to just love being the exception. And that element is boron. Okay, so let's dive right in and meet this family. You'll see it listed as group 13, but it also has a pretty cool name, the Ionisation. So let's get introduced to the whole crew. So here they are running right down the column on the periodic table. You've got boron at the top. That's our main character today. Then comes a very familiar face, aluminum. And as we go further down, we get the heavier guys, gallium, indium, and thallium. So what exactly makes them a family in the chemical sense? Well, it all comes down to this, their outer electron configuration. Every single one of them has 2 electrons in their outer s orbital and just 1 electron in their outer p orbital. Think of it like their shared chemical DNA. It's that one defining trait that puts them all in the same column on the periodic table. Now, usually with any chemical family, you expect to see some really predictable trends as you move down the group, right? Things like atomic size, how reactive they are. It should all follow a nice, smooth, logical pattern. But with this group, yeah, things get a little weird. The rules start to get blurry. Okay, check this out. We're looking at ionization enthalpy. That's basically just the energy it takes to rip an electron away from an atom. And just like we'd expect, the energy drops a lot, from boron to aluminum. Easy peasy. But then, look what happens. It just flattens out. For gallium, indium, and thallium, there's almost no change at all. That is not the smooth downward trend we were looking for. So what on earth is going on here? Well, the culprit here is something called pore shielding. You see, as you get to the heavier elements in this group, they start filling up these inner d and f orbitals. And the thing is, these orbitals are, well, they're terrible bodyguards. They do a really bad job of shielding the outermost electrons from the super strong positive pull of the nucleus. So that extra pull kind of cancels out the fact that the electrons are further away, and it just totally messes up our nice, neat trend. And this leads us to a really important idea for these heavier elements, the inert pair effect. It sounds complicated, but the idea is simple. Because those 2 s electrons are being held onto so tightly, they just get lazy. They become inert. A lot of the time, they just can't be bothered to get involved in chemical bonding at all. And this right here shows you the result perfectly. Look at aluminum. For it, the most stable thing to do is lose all 3 of its outer electrons and form a +3 ion. Simple. But then you go all the way down to thallium. That inert pair effect is so strong that thallium prefers to just lose that one lonely p electron. So its most stable state is +1. That's a complete reversal of chemical personality as you go down the group. So, okay, the heavy elements have their quirks, but all of this is really just the opening act. Now we get to the main event, the ultimate anomaly of the group, boron. It doesn't just have quirks, it plays by a completely different rulebook right from the start. So why is boron such a weirdo? Well, it really boils down to a few key things. First, it's incredibly tiny. Second, it holds onto its electrons with an absolute iron grip. That's the high ionization enthalpy. It's also pretty electronegative. And maybe most importantly, it has no d orbitals to play with in its valence shell, which really limits the types of bonds it can make compared to the rest of its family. I mean, the biggest, most fundamental difference is this. Boron isn't even a metal. It's a metalloid, which means it's kind of stuck in the middle with properties of both metals and nonmetals. Every other member of its family, aluminum, gallium, all the way down, they are all classic reactive metals. Boron just fundamentally does not belong. And what's really wild is that because boron is such an outcast in its own family, it actually has more in common with its diagonal neighbor, silicon, over in group 14. Seriously, they both form acidic oxides, they both form similar covalent hydrides, their halides react with water in the same way. It's like boron decided it likes the family next door better and just started copying them. Okay, so we've established that boron is a total rebel. So what happens when this rebel actually starts forming compounds? Well, as you can probably guess, the molecules it builds are anything but ordinary. Let's kick things off with a little chemical puzzle. Take a look at this molecule, diborane. It's got 2 boron atoms and 6 hydrogen atoms. Now, if you do the math and count up all the valence electrons they have to share, you only get 12. But to stick all 8 of those atoms together with normal bonds, you need 14 electrons. So how in the world is this thing holding together? It's short 2 electrons. It can exist because it's part of a special class of molecules called electron-deficient compounds. And the name says it all. It's a molecule that literally does not have enough electrons to form normal bonds between all its atoms. It has to get creative. And boron is an absolute master at this. All right, let's solve this diborane puzzle. The first part is pretty straightforward. The 4 hydrogens on the outside, 2 on each boron, they form perfectly normal bonds. You know, the standard 2-center, 2-electron bonds we all know and love. Okay, so that accounts for 8 of our 12 electrons. We're left with 4 electrons, but we still need to connect the 2 boron atoms and 2 more hydrogens. How do we do it? And this is where the magic happens. Here is the beautifully weird solution. Those last 4 electrons form 2 amazing, bizarre bonds that actually bridge the 2 boron atoms. Each bond uses only 2 electrons to hold 3 atoms together, a boron, a hydrogen in the middle, and the other boron. It's called a 3-center 2-electron bond, or as chemists lovingly call them, banana bonds. It is such an elegant way to solve an electron shortage. All right, let's look at another one of boron's strange creations, boric acid. Now, we all know it's a weak acid, but in true boron fashion, it doesn't act like a normal acid. Its whole method of being acidic is completely unconventional. See, your typical acid, right, it donates a proton, an H+, to water. Boric acid, it does the exact opposite. Instead of giving anything away, it aggressively takes something from water. It reaches out and just plucks a hydroxyl ion, an OH-, right off a water molecule. And that is what leaves behind the extra H+ that makes the solution acidic. So clever. This behavior makes boric acid the textbook example of what we call a Lewis acid, which is just a fancy way of saying it's an electron pair acceptor. And this, right here, is the core of boron's entire chemical personality. Because its compounds are almost always electron deficient, they are just hungry for electrons. That makes them incredible Lewis acids. And here's the perfect demonstration of that in action. You have boron trifluoride, which is super electron deficient, and then you have ammonia, which has this lone pair of electrons just hanging out, not doing anything. So when they meet, the ammonia is more than happy to donate its electron pair to the empty orbital on boron. And just like that, they form a new bond, and boron's hunger for electrons is satisfied. It is a classic Lewis acid-base reaction. So there you have it. Boron really is the undisputed rebel of group 13. It completely ignores the family trends, it acts more like its neighbor, and it builds these wonderfully bizarre molecules that force us to rethink the rules of chemistry. And that kind of leaves us with one final thought, right? The periodic table is all about patterns and predictability. But a lot of the time, the most fascinating chemistry, the really cool stuff, happens with the exceptions. So if boron is this weird, it makes you wonder what other rebels are hiding out there in the periodic table, just waiting for us to find them.